Okay, we will go live, go live. All right, everyone, we are live this afternoon. Good afternoon, NOVA fans, and happy Thursday. My name is Gina Varamo, and I am the Outreach Manager for NOVA Education. I am thrilled to be joining you today for the second event in our NOVA Universe Revealed virtual field trip series. NOVA Universe Revealed gives users a ringside seat into moments when the cosmos changed forever, like the birth of a star in the stellar nebula or the chaos created as two black holes collide. And while we maybe made some, pretty cool animations in NOVA Universe Revealed about the first light in the Big Bang, but today we're going to learn about the hunt for the real thing. So if you've been following space news, you may have heard of a little project called the James Webb Space Telescope. This orbiting infrared observatory is on the hunt for the first galaxies or luminous objects formed after the Big Bang, and will observe the formation of stars from the first stages to the formation of planetary systems, just to name a couple things that this telescope is aiming to do. So I'm honored to welcome our special guest, Dr. Jonathan P. Gardner, Chief of the Observational Cosmology Lab at NASA's Goddard Space Flight Center and the Deputy Senior Project Scientist for the James Webb Space Telescope. He leads a group that studies the universe as a whole, from its dramatic beginnings in the Big Bang to the mysterious dark energy that will determine its future. He's kind enough to join us just 1 week before James Webb is scheduled to launch to tell us more about the project. So at any time during this presentation, if you have questions for our guests, please, if you're in Zoom, drop them in the Q&A section. You can find it at the bottom of your screen. Or if you're joining us on Facebook or YouTube, you can put it into the questions or into the comment section, and we'll try to get to as many as possible throughout our time together. So without further ado, Dr. Gardner, I'm going to pass it off to you.
Okay, thank you. And I'm happy to be here talking to all of you. I'm going to share my screen so that you can see some pictures and some videos. So how does that look?
Beautiful.
Okay, I'm going to be telling you about the James Webb Space Telescope, and just a little giveaway. If you want to learn more after the end of this talk, we have a website, web.nasa.gov, and if you want to stay up to date on breaking news in the mission, we have a blog, blogs.nasa.gov/web. So what is the James Webb Space Telescope? It's a large, cold telescope in space, or it will be after we launch it into space. Webb is the successor to the Hubble Space Telescope. Successor, not replacement. We'd love to have the two of them working together, which we expect to have. It's a joint project of the world. It's NASA working with the European Space Agency and the Canadian Space Agency to put it together. And it's going to be launched on Christmas Eve, just a little bit more than a week from now, 7:20 in the morning on December 24th. So when we first started using Hubble and started thinking about what we would do next, we're thinking about the science that we wanted to do. And Webb is about the origins and evolution of galaxies, of stars, of planets, and the conditions for life on those planets. So all about origins. This picture is the faintest picture that humanity has ever taken. It's called the Hubble Ultra Deep Field. And we took the Hubble Space Telescope and we stared at one mostly empty part of the sky for more than a month and kept going back to that same field over the course of the 30 years that Hubble has been working. We spent almost a full year of that time looking at this place in the universe and the region around it. Now with this Hubble Ultra Deep Field, we're seeing the faintest things that we can see. And faint means that they're far away. And far away means that it takes most of the age of the universe for the light to get from those galaxies to us, to our telescopes. So when you look at this picture, almost everything you see in it is a galaxy. There's a couple of stars that are in our galaxy, but most of these things are distant galaxies. And the ones that look like pretty spiral or elliptical galaxies like we see today, those are the relatively nearby ones. If we zoom in, the very faintest reddest smudges in this image are the ones that are the furthest away. These galaxies are so far away that their light has been traveling since less than 1 billion years after the Big Bang. Now, the universe is 13.8 billion years old. So the light has been traveling for most of the age of the universe. We're seeing these galaxies when the universe was young. And we would like to see the first galaxies that's formed in this region, because when you understand how something starts out, it's much easier to make a picture of how it changes over time from when it was first formed to the present day. But when we look at these galaxies in this field, the faintest galaxies that Hubble can see, some of those galaxies are already several 100 million years old when we're seeing them. So in order to see the first galaxies that formed in the early universe, we have to go further back in time than Hubble can do. We have to find galaxies that are fainter than Hubble can see, even with all of the observing time we've spent with Hubble in this field. So that's what led us to realize that we needed a telescope that was bigger than Hubble to do this task. It also needs to go into the infrared, because as that light is traveling through the universe is expanding and the light is being stretched out. So wavelengths of light that start out as blue light or even ultraviolet, which is bluer than we can see, get stretched out over time, pushed into the red or even into the infrared. So what we need is an infrared telescope that's bigger than Hubble. And that's what Webb is all about. So here's a comparison. Hubble is on the left. Hubble has a primary mirror that's 2.4 meters. That's just a little bit bigger than a person standing up. And the Webb mirror is 6.5 meters in diameter and is made up of 18 individual hexagonal mirror segments that all have to work together perfectly as a single mirror to collect all of the light. The reason why we make it out of mirror segments is to make it lighter. So we can put a big telescope into the same size rocket that could only lift a smaller telescope if it was a single piece of glass like the Hubble mirror. So it's bigger. And another thing you see there is that Hubble has a tube around it, but Webb has a 5-layer tennis court sized sun shield to protect it from the sunlight. So Hubble is in what's called low Earth orbit, and it's kept at room temperature. For one thing, we sent the astronauts up on the space shuttle to fix Hubble several times. And you don't want the telescope to freeze the astronauts when they get there. But also because Hubble is in orbit around the Earth, it's going in and out of sunlight every 90 minutes. And so we use heaters to kind of keep it at room temperature. But in order to have an infrared telescope, the telescope itself has to be cold enough that it's not emitting infrared light itself, because infrared is basically heat radiation. So while Hubble is kept at room temperature, we put Webb behind this sun shield so that it can cool down to 370 degrees below 0 Fahrenheit. That's minus 225 degrees Celsius, or about 50 degrees above the absolute zero. So 50 on the Kelvin temperature scale. Another difference between Hubble and Webb is that while Hubble is in orbit around the Earth 375 miles up and was launched on the space shuttle, which is about as high as the space shuttle ever went, we're going to put Webb 1 million miles away from the Earth. That's 4 times the distance from the Earth to the moon. And it's a special point, a special orbit in which, as the Earth goes around the sun once per year, Webb is going to go around the Earth and the sun once per year. And the sun, the Earth, and the telescope are always kept in a line. So as you imagine the Earth going around the sun, the Earth's gravity kind of tugs a little bit on Webb, and so Webb can keep up, even though it's further from the sun than the Earth. Webb can keep up and keep in a line, and both the sun and the Earth are always on the warm side of that 5-layer sun shield, and the telescope is on the cold side, always protected from the sunlight and from the Earth light. Now, when we build a giant infrared optimized space telescope to find the first galaxies that formed in the early universe, it also turns out that that same telescope will be really good at seeing stars and their planetary systems form within our own galaxy, the Milky Way. So this is a picture of a dusty cloud where stars are forming, but the stars are forming inside those pillars of dust. And when we look in visible light, all of the light from the actual forming stars is absorbed by that dust, and we can just see the outlines around it. As we go into the infrared, the longer wavelengths we are able to start to see through the dust clouds into where the action is happening and the stars and planets are actually forming. This is a Hubble picture. Hubble can see a little bit into the infrared, but Webb can see much further into the infrared, much longer wavelengths, much redder light, and we'll be able to see right down into where these stars and planets are forming. Another really exciting thing that Webb will do will be studying the atmosphere of what we call exoplanets, planets that are in orbit around other stars. One such system is the TRAPPIST-1 system, which has a total of 7 planets that we know about that pass in front of their star. So down, if in the lower left, you can see a movie. In this movie, this is actually a movie of the moon crossing across the face of our sun. Now, for the moon and the sun, when this happens and you view it from Earth, it's called a solar eclipse. And the moon is about the same size as the moon appears to us as the same size as the sun, and it completely blocks the face of the sun. But this movie was not taken from the Earth. It was taken from one of our sun observing satellites. And so in this picture, the moon appears much smaller than the sun. Now, when this happens with distant planets, a very special thing happens. The light from the star goes through the atmosphere of the planet and reaches our telescope with information about the constituents of that atmosphere, what it's made up of. And if we have an infrared telescope, we can learn about the molecules in the atmosphere of that planet, things like methane or water. And we can learn about the planets that are in orbit around other stars, both the gas giant planets that are like our own Jupiter and Saturn, but also small rocky planets like the Earth with atmospheres that can indicate whether the conditions or the constituents that might be necessary for life on other planets, whether these planets have those things in their atmosphere. Now, Webb's probably not going to be big enough that we can tell whether there is life on other planets, but it's a very important step in the path to finding the conditions. How common are the conditions for life on other planets? And in particular, are there planets out there that might have oceans, liquid water on their surface, which is on the Earth anyway, is an important part of life on Earth. And then within our own solar system, because of this big sun shield, Webb can't point directly towards the sun, and so we can't observe Mercury, Venus, and the Earth. But the outer solar system, we can observe all of the planets. So with Mars, Jupiter, and Saturn, it might be hard to take pictures because they're so bright and Webb is so sensitive. But we can do things like break up the light into the constituent wavelengths using a technique called spectroscopy and learn about the outer planets, but then also especially the moons of the outer planets and things like Pluto, the dwarf planets Pluto and Eris in the outer solar system, and comets and asteroids. And the very outer reaches of the solar system hold pristine material from the dust cloud that formed our own sun 5 billion years ago. And Webb will be able to study those things in the outer solar system and learn about the formation of our own solar system and our own history. Because that's what Webb is all about, connecting the Big Bang to the Earth, connecting the formation of the stars, the formation of the galaxies, formation of stars and their planets, the formation of planets around other stars and whether they might have the conditions for life, and then the history of our own solar system. So now I'm going to tell you a bit about the hardware, all of the pieces that we have built on Webb over the course of the last almost 20 years, putting it all together. This is a picture of the 4 cameras, kind of a family portrait of our cameras. This whole thing is bigger than a person. It's about 2 meters on a side. So these are really big cameras. We have the near-infrared camera, which is our main imager. The near-infrared spectrograph is contributed by the Europeans. The fine guidance sensor and the camera called NIRISS was contributed by the Canadians. And I know we have some Canadians watching, so thanks for giving us that camera. And then finally, the mid-infrared instrument observes the longest wavelengths. So when you think about how you build a space telescope, there's several things that you have to think about. First of all, you're putting it on top of a rocket and it has to survive the launch. And the launch introduces lots and lots of sound and lots of vibration into the payload. So we need to make sure, we need to test everything so that it will survive the launch. And then we also need to test it in the vacuum of space and at its operating temperature. And the way we do this to ensure that it'll work, because we can't go out into space to fix this one, we put together a little component, we test it to see if it works. We then simulate launch with acoustic and vibration tests, and you saw the vibration test of one of our mirrors. And then we test it again. We see if it still works after shaking it and blasting it with sound. Then we assemble it into the next higher level, like we put the detectors into the camera and we go through the process again. Then we put the camera into the instrument compartment and we test it again. Assemble it up until the very highest level, repeating until we are all complete. This is a time-lapse video of putting together the primary mirror with the 18 mirror segments. Each of these segments is made of beryllium, which is a very lightweight, stiff metal that holds its shape at cryogenic temperatures well below freezing. And these 18 mirror segments were put on with a black protective cover over each of the segments while we were assembling it. The beryllium mirrors are coated in gold because gold reflects infrared light very well. So that was putting together the mirror. Here's another kind of close-up of the robotic arm that assembled the mirror together. And then This is the secondary mirror. So the light comes from the distant galaxies, bounces off the primary mirror to the secondary mirror, then bounces off the secondary mirror down into the instruments. When we had the telescope all assembled together, we took off the black protective covers, and you can see the gold-colored mirror. This is a pretty cool picture because taken in the clean room at the NASA's Goddard Space Flight Center where I work, because the photographer lined up the NASA logo on the wall to be reflected in the mirror. Now, one of the things you can see is that the logo is distorted, and that's because this is not a flat mirror. It's a focusing mirror that focuses the light onto the secondary. And that means that the logo is distorted. And then there are some of the people that the technicians that worked in the clean room. They're all wearing what are called bunny suits, the white protective suits over their clothing. They've got gloves. And these are people that wore masks before wearing masks was cool. In that case, it's to protect the mirror from the kind of dust and condensation that people bring around with them. And this is the coolest selfie that I will ever have and take in my life. This is a picture of me reflected in the primary mirror of the Webb telescope. I was not in the clean room itself. I was in the viewing window, but able to see my reflection in the mirror. After the mirror had been all put together and the instruments had been all put together, we needed to assemble the instruments onto the back of the telescope. And here is a time-lapse video of that happening. You can see the viewing window in the upper right, and right at about this point is when I arrived at the viewing window. So I got to see this go in live, this installation. A lot of people involved in putting these things together. There's not only the people that are actively working on it, but there's a lot of people who are watching, just each watching their part of the components to make sure that things don't bump or go into the wrong place. With the telescope and instruments all assembled together, we needed to put it through a test. We needed to take it to the vacuum of space in a vacuum chamber and bring it down to its operating temperature. We did this in a historic vacuum chamber that's at the Johnson Space Center in Houston, Texas. Now, this vacuum chamber is 12 meters in diameter and 35 meters high. It's huge. And it was originally built in the 1960s for the Apollo astronauts to practice walking on the moon in their spacesuits in a vacuum. So this vacuum chamber had a simulated lunar surface on the bottom of it, and the astronauts would go in their spacesuits and they'd pump out all the air and they'd practice walking around on the moon. Round about 2012, the James Webb Space Telescope project took over this vacuum chamber. We took out the lunar surface. We also installed an inner shroud that used liquid helium to cool down to the temperatures, the operating temperatures of Webb, 225 degrees below 0 Celsius. And then we put the Webb in there with its mirrors and the cameras, and we shined light on the primary mirror and it bounced through all of the optics into the cameras. And it was a test that everything worked. All the cameras operated and the telescope worked perfectly as well. For those of you who can remember it, this actually we had Hurricane Harvey come through during this 3-month-long test, and that had 51 inches of rain in the Houston area, but the Webb telescope was kept safe, and the people that were doing the test managed to keep going, even though the whole place was being flooded, or the surrounding area was being flooded with all of that rain from the hurricane. So there was kind of some heroics involved in keeping that test going. Meanwhile, out in Los Angeles at the Northrop Grumman facility, we were putting together the spacecraft and the 5-layer sun shield. And here you can see the spacecraft and the sun shield with just a model of where the telescope would go in the middle. But then we needed to put the two halves of the mission together. So there you see the telescope on the right and the sun shield on the left. And here's a video of assembling the two together. The whole observatory is about 6.5 tons, 6,500 kilograms. And we're assembling the telescope onto the spacecraft. The spacecraft is the box down below the sun shield that maintains the position in orbit and also communicates with the Earth. So we take our data in the telescope and we send it down to Earth for the scientists to analyze. The last thing you see here is separating the 5 layers of the sun shield. That was a deployment test. I'll show you in a minute that we're going to actually be doing that out in space, pulling out the sun shield like that and separating the 5 layers. The 5 layers, each one is colder and colder as you get towards Webb, and there's vacuum in between them, so all of the heat can escape in between the layers. And so we have full sunlight on one side of that sun shield, and the telescope is 225 degrees below zero on the other side. That's an equivalent SPF of 1.5 million if it were sunscreen. So there's a picture of the telescope on top of the sun shield, fully assembled together. You can see the 2 side wings of the primary mirror are folded back. We do that for launch, and that will be folded out into a single mirror after launch in space. And then likewise, the secondary mirror is up at the top, but that is supported by 3 poles, and those will also fold out after launch. Here's a picture to show you the scale. There's a technician there on top of the crane and the 6.5 meter or 6.6 meter mirror up near the crane. So then we folded it all up and we were ready to ship it to the launch site. The launch itself is being provided by the European Space Agency and an Ariane 5 rocket, and that launches from French Guiana in South America. And so to get there, we put the Webb on this boat and we shipped it through the Panama Canal. You can see it going there, the boat going there through the Panama Canal on the left, and arriving in Kourou, French Guiana, South America, in the among the palm trees and tropical birds of French Guiana. And then Christmas Eve, 7:20 a.m. Eastern Time, we'll have the launch. Now you can watch this launch on the web, of course, through NASA TV. You'll need to get up pretty early if you're on the West Coast, because that's 4:20 a.m. Pacific time, but that's when it happens. And Webb will be launched out into space and sent on its way to the second Lagrange point for its operating mission. Now, I alluded to this before, but the whole thing is folded up before launch because we have a 6.6 meter telescope and the Ariane 5 is a 5 meter diameter rocket. So just immediately after launch, we fold out the solar array and the communications antenna. And then we have to start folding out the 5-layer sun shield. There are some protective covers. It's shown in pink in this video. This is an animation, of course, done by computers. The real thing will be taking place over the 2 weeks after Christmas. So we fold out we remove the protective covering and start pulling out the side wings of the sun shield. The sun shield itself is made of something called kapton. It's kind of a plastic material, not real strong. So it's held on the outside with cables. Separate the 5 layers. And then the last deployments are the secondary mirror and the 2 side wings of the primary mirror. All of this takes about 2 weeks, and then we spend another 2 weeks moving the primary mirror segments off of their launch configuration, the kind of protective padding. And then after that, it will actually take us 5 more months before we're ready to go with the science. So commissioning is a 6-month process. We have the first month is all the deployments and arriving at L2 and cooling the telescope to the point where we can turn on the cameras. We then have 3 months to line up those 18 primary mirror segments so that they are a perfect optical surface, a perfect mirror. We need to line that up to the point where if that telescope were spread out to the size of the United States, it would need to be lined up to within about 3 feet. So that's how precise it is. A total alignment of 150 nanometers accuracy. And then 2 more months to turn on the cameras and check them all out. And then 6 months after launch, should be the end of June, maybe beginning of July next year, we'll start to get the science pictures. So here's a model of the telescope as it looked like in 2005. I'm down here in the front row, and here is the picture of the telescope as it actually existed in 2020. Now, you might be interested in learning more about Webb. So on the right, we have the Webb blog, blogs.nasa.gov/Webb. We have our website, web.nasa.gov. There's Twitter and Facebook and YouTube and Flickr and Instagram. All of the videos and photos that I've showed you are available either on the YouTube account or on the Flickr account, and there are thousands more. So if you'd like to find out more about Webb and to watch as we make progress, you can follow us on the various social media. And then watching the launch itself, it's going to be carried live on NASA TV. There's the link. You'll also be able to see it on the news. I think they'll probably show it, but we'll have a video on YouTube. There are local events planned throughout the United States, both launch day and afterwards. And there's everything you need to know. We have that web.nasa.gov content, web launch, need to know.html. So I'd like to thank you all for joining today. And I think there might be some questions.
Oh, we have questions. Thank you so much. We have great questions that we're going to start asking. And if you have any more, feel free to drop them in the chat, and then we will try to get to as many as we can. So we have a few student questions, and a popular student question was, can this telescope be used to see event horizons on black holes?
So good question. Astronomers using a network of telescopes on the ground across the whole Earth managed to take a picture of a black hole. That was using a type of light that's called microwaves or far infrared, and it required the baseline of the whole Earth, essentially a telescope the size of the Earth to see that that image. Now, Webb is not going to be able to take a picture of a black hole like that, but it will be able to tell us a lot about what's happening around the black hole. So black holes emit light when stuff falls into them, it's either it comes out as X-rays, because as materials falling into the black hole, it gets so hot that it emits X-rays. But some of that light is absorbed by dust and comes to us is re-radiated as infrared. So there's a lot that Webb can tell us about black holes, but it's not the telescope to take pictures of them.
So that actually we have another student question that's very similar. Will Webb produce pretty pictures like Hubble, which are very engaging, or will it being infrared, will it really focus on data?
So it will produce pretty pictures. They're not going to be, well, so Webb can see some visible light, but mostly what we do is we read out the pictures in the computer, and we can just substitute the wavelengths of light that we can see for the infrared light. So the pictures will look a bit different from Hubble because they're seeing different parts of the same objects, but they will be just as pretty. Yeah, what matters when you're looking at gorgeous pictures in astronomy is, do you have lots of pixels? Do you have sensitivity? And can you see the different structures within the galaxies or the star-forming regions? And Webb has all of that, like Hubble. So it will take really nice pictures, and you'll enjoy watching them, looking at them. Plus, it also tells us the science of what's really happening.
Win-win, right?
Yeah.
Pretty pictures and data.
Yeah.
Fantastic. We have a couple of students are also curious to know, how far can the telescope see and take photos?
Right. So what matters for how far away it can see is essentially how close to the Big Bang can we get. So we're looking backwards in time as well as looking across the universe. And there is a limit when we are looking so far backwards in time that we get to the Big Bang. So Webb is designed to look back to maybe within 100 or 200 million years after the Big Bang, and that light has then been traveling for 13.6 billion years out of the 13.8 billion years that the universe has existed. So it's almost all the way to the edge of what we can see. So that's the answer. We're hoping to be able to see back 13.6 billion light years away. Now, it's a little bit more complicated than that, because as that time is going on, the universe itself has been expanding. And so the things that emitted that light are now further away from us than they were when the light was emitted. But that's essentially what it is. We're looking back, we're looking so far away that we can see back to when the universe was really young.
That's so cool. And just is kind of crazy that we know how to do that.
Yeah.
So we have another question from a viewer that wants to know, in a similar vein, could those faintest galaxies have moved and now we might see them in a different part of the universe because they're brighter or they changed in brightness?
So we can see each thing just where it was when it emitted the light. So we don't see things where they are now because we would need to wait for that light to get to us. This is hard to kind of get your head around, but basically, if you're looking at the sun, you see the sun the way it was 8 minutes ago, because it took 8 minutes for the light to get from the sun to us, to the Earth. If you're looking at the nearest star, that's about 4 light years away. So we see it the way it was 4 years ago, but we can't see it the way it is now without waiting for 4 more years. And likewise, if we're looking at these very, very distant galaxies, we're seeing those galaxies the way they were billions of years ago, and we can't see them the way they are now without waiting for billions of years. So building up the whole picture of how galaxies change over time, we're not actually looking at the same galaxy changing. We're looking at baby galaxies and comparing them to, kindergartner galaxies that Hubble can see, and compared to fully grown adult galaxies. But they're different galaxies, so we have to use statistics to build it up into a picture of how galaxies change over time.
So, hypothetical question from an audience member. Say aliens had James Webb or a telescope similar. Would they see dinosaurs on our planet if they pointed it to us because the light is so old?
They could. I mean, I would say that Webb is not big enough to actually see animals individually, but yes, aliens using a telescope to look at the Earth, if they're looking at the Earth from millions of light years away, they would see the light that was emitted millions of years ago. And so this, again, if it depends on where they are. If they're just 10 light years away, then they would see light that's only 10 years old. Or if they're like monitoring radio transmissions from the Earth, they might get, the early days of radio if they're 100 light years away, or maybe they would get television if they're 50 light years away.
Oh man, I hope it's something good. There's a lot of junk out there. We have another question, some more specific questions about the telescope too. So what are the chances of space objects damaging the telescope?
So that's not something that's very likely. Most of space is very, very empty. So there's very little stuff out there that could run into it, especially out where Webb is going. The second Lagrange point is not a place where stuff accumulates. Actually, the fourth and fifth Lagrange points would not be a good place to put your telescope because stuff falls into there and stays. But second Lagrange point is pretty empty. Stuff kind of falls away from it. And we do have to worry about particles, atomic particles, stuff coming from the sun. That does go through the telescope and the sun shield, microscopic particles. And we just kind of take that into account. And we make sure that our electronics will work, even with some radiation out there. But generally, space is very empty and there's very, very little chance of anything running into it.
Great. And then, so another similar question is, if anything happens to it while it's in space, can it be fixed?
No.
Oh boy.
So that's why we test it so much, is because when it's going out there, it just has to work. We don't have any way of getting out there and fixing it. Hubble was a little bit unusual in that sense. Hubble's was built to be serviced or to have repair missions with the astronauts on the shuttle going up there and fixing stuff. And that's one reason why it's lasted as long as 31 years since its launch in 1990, which I imagine is Hubble's older than a lot of the people listening in here.
Yeah.
But the last servicing mission to Hubble was 2009, and there's not going to be any more. So, but most of NASA's science missions, like the Mars rovers, we sent the rovers to Mars, and they worked longer than we were planning for them to work. And likewise, we're putting Webb out there after an awful lot of testing to make sure that it's going to be okay and it's going to work. But we don't have any way of getting out a million miles away to fix it.
Right. We have another student question that wants to know, how do you physically watch the telescope when it's in space?
So you probably can't actually see it out there. So we communicate with NASA will communicate with the telescope using radio.
Mhm.
We use what's called the Deep Space Network, which is a network of 3 giant radio dishes around the world, 70 meters in diameter. And we can send the commands to the telescope, and the telescope will send back the data and what's called the telemetry, which is sort of things like what temperature is it right now, and how are things working on board. But in terms of, unfortunately, we don't have any way of watching the deployments directly. There will be another computer animation that will be updated as we do those deployments on our website, but we don't have a camera on board that can see it. For one thing, it's in the dark.
Right.
As soon as we've got the sun shield out there, it's going to be very dark and very cold, and we will know what state it's in because we have lots of sensors on board, but we don't have any actual pictures. And people with a really serious telescope might be able to find it and take a picture, but it would just be a dot, but it's actually pretty faint. It'll be fainter than Pluto, and Pluto's hard for amateur astronomers to find. So
it won't be like how astronomers could see like the International Space Station.
Yeah, you can see the International Space Station going over. Occasionally, people can pick up Hubble because that's in low Earth orbit. But Webb is going to be so much further away that it'll be really faint, and you can't see it without a really pretty big telescope.
Yeah. We have some folks that would like to know what's the expected usable lifetime for the telescope? How long will it be in use?
So good question. There's only one thing that gets used up, and that is fuel. We have some rockets on board, and we use fuel both to get it into the final orbit, and then we have to use fuel about every 2 to 3 weeks to maintain that orbit, to keep it in its position around L2. And then also the sun shield acts like a sail. It's a solar sail. And as we point the telescope different directions, what's called angular momentum builds up. And we need to use the fuel to counteract that so that the telescope doesn't flip over. And again, that's something we need to do every 2 to 3 weeks. So we need fuel, and we have a pretty big tank on board. It's designed to have 10 years of fuel in it, but it actually turns out that with a little bit of luck, we can get fuel. We will have fuel for a lot longer than that, because about half of the fuel is used just to get to L2, to tweak up the orbit.
Right.
And so an awful lot matters with how well the rocket works in the launch. So if the rocket works perfectly, we will have lots of fuel left over. If the rocket's a little bit low from what we want it to do, then we need to use our onboard fuel to make up for that. And we should still get 10 years, but it might be more tight than that. So anyway, the short answer is that it should be at least 10 years before we run out of fuel. Could well be a lot longer than that, like 15 or 20 years. And then what it comes down to is how long will it just keep working? Or will something end up breaking?
Yeah. That this kind of is a similar question too. So I'm thinking it's related to fuel and everything. Is there a specific reason why the launch is from that area of the world and at that specific time?
Yeah, so it has to do with the Earth spinning around its axis. So that spin gives the rocket a little bit of an extra boost, but you have to be launching in the right direction. So the Earth spins from west to east. That's why the sun rises in the east. So as the Earth is spinning, if you're launching towards the east, then you have that extra boost. And also, the Earth spins faster at the equator than it does at other latitudes. So you want to launch towards the east near the equator. And then you want to have your spaceport on the east coast of your continent so that you can launch your rockets out over the ocean and not over people where you might drop some stuff on the people. So all of that leads to you want your spaceport to be on the east coast of relatively near the equator. So the United States NASA launches are from Florida, which is relatively close to the equator on the east coast of Florida. But Webb will be launched on a European rocket, and the European launches are from French Guiana, and French Guiana is actually part of France. So it's a French launch from the east coast of South America.
Great. I think this is a great question. This project has been going on for so long. I mean, we saw that photo in 2005. I mean, earlier we had talking about this from the early 90s. How do you keep up with the development of new technologies as you're working on this project? So did you keep upgrading the equipment, or is the technology 20 years old at this point?
So not 20 years old, but 5 to 10. So that is just one of those things about putting things in space, is that it does take a long time, and you do have to freeze in the technology at the point at which you put it together. And you still have this long testing phase where you need to make sure it works when it gets there. So one of the important things are the detectors in the camera. These are really, really sensitive detectors, infrared detectors, and those got put into the cameras in sort of the 2013, 2014 timeframe. So in that sense, the next mission will have better detectors, but that's just kind of one of those things that you have to do when you're building space telescopes. One of the consequences of that is that we don't do anything in space that can be done with telescopes from the ground. So Webb is not designed to just be a little bit better than the ground-based telescopes. It's designed to do very different things, and anything that can be done, even with a giant, like a 30-meter telescope or 25-meter telescope that are being built, if that can be done with a ground-based telescope, we didn't design Webb to do it. It has to take advantage of the unique properties of being in space, of being able to be that cold and not have like the atmosphere freeze onto your mirror, like what happened if we tried to do something this cold on the ground. So needs to be unique.
Right. Great. And I'm sorry, we have so many more questions, but we're going to ask our last question. And this is a question from a student who wants to know, what is it like to be a space scientist?
It's fun. I get to think about the universe, and I get to talk to people like you. But I think that when you make a discovery about how things work, that is a wonderful feeling. When you can understand something that nobody's ever known before. And the first time we take images, science data with Webb, again, probably late June, early July, we're going to find out about things about the universe that nobody ever knew. And over the course of the first year, we already have a plan for all of the things we're going to look at. And it's all of the things I've talked about, very distant galaxies, stars and planets forming, planets around other stars. And some of those things are going to surprise us. We're going to find out things that just nobody predicted. And that's just really exciting.
Yes, that is so exciting. And, we're leading up to a super exciting time. It's almost launch. Thank you so much for taking time to be here and joining us today and answering all of our questions. I'm sorry we couldn't get to all of them, but I highly encourage you all to check out the website and social media channels, and perhaps you can get some of your questions answered there. So thank you, Dr. Gardner, for joining us today and answering our questions. Thank you to our viewers for your engagement and your questions. Without you, this conversation wouldn't have been possible. And if you want to learn more about the universe and are interested in some NOVA content, all 5 episodes of NOVA Universe Revealed are available to stream right now on NOVA's website. That's pbs.org/NOVA. If you're looking for a new series to binge over your holiday break, this could be the perfect opportunity. So go ahead and do it. Our final NOVA Universe Revealed field trip will be in the new year and talk all about exoplanets. So if you want to brush up on your exoplanet knowledge, you can play the NOVA Exoplanet Lab beforehand. Follow NOVA Education for updates and registration links so you don't miss a thing. And with that, thank you for watching. We hope everyone has a safe and healthy holiday season, and we will see you at the next field trip. Thanks again. Take care, everyone.